All right, welcome back to AI.Code.Cast. Today we're doing a deep dive into a coding challenge that's notorious for tripping people up. It's called the triangle problem.
Yeah, it's super popular on LeetCode.
And it's not just some abstract brain teaser.
Right.
It actually connects to real-world problems, like navigation apps, finding the fastest route.
Or figuring out the most efficient way to allocate resources, that sort of thing.
Exactly. Now, I gotta say, I tried this problem a while back, and let's just say dynamic programming, and I weren't exactly best friends at that point.
Well, hopefully by the end of this deep dive, you'll have a newfound appreciation for it.
Fingers crossed. So let's jump right in. What exactly is this triangle problem all about?
So basically, you're given a triangle made of numbers.
Okay, like a pyramid of numbers.
Yeah, kind of. And your goal is to find the path from the top to the bottom that has the smallest sum.
That sounds simple enough.
The catch is you can only move directly down or diagonally to the right.
Ah, so no zigzagging back up the triangle.
Exactly. You have to pick one number from each row as you go down.
I see. So I could imagine for a small triangle, you might be able to just eyeball it and find the best path.
Yeah, but imagine a triangle with like hundreds of rows.
Oh, yeah, that'd be a nightmare.
Exactly. And that's where the brute force approach, where you try every single path, just falls apart.
Right, because the number of possible paths would explode exponentially.
Precisely. The time complexity gets out of hand really quickly.
Okay, so brute force is out of the question for anything but the tiniest triangles.
Yeah.
That's where dynamic programming comes in.
Oh, got it. We're going to break down a super efficient solution, bottom-up dynamic programming with space optimization.
All right, before we get into the fancy solution, let's break down why brute force is so bad. Walk me through how it would even work.
Sure. So with brute force, you start at the top of the triangle. You have two paths you can take to the next row, right?
Down or diagonally, right?
Right. So you basically explore both of those paths. And then from each of those points, you again have two paths to the next row and so on.
You're basically creating this massive tree of possibilities.
Exactly. And it gets out of control really fast. Like even for a triangle with just 5 rows, you'd be dealing with 16 possible paths.
Oh, wow. And if you increase that to like 10 rows?
You're looking at over 1,000 paths.
Okay, brute force is definitely not going to cut it. So dynamic programming, what is it exactly? Because I got to admit, it sounds a little intimidating.
It's not as scary as it sounds. The main idea is to break down a problem into smaller, overlapping subproblems.
Subproblems, huh? Okay, and why do we care about those?
Because instead of solving the same subproblem over and over again, we can store the result the first time we calculate it.
Oh, I see. So kind of like a cheat sheet for our code.
Exactly. And then we can just look up the solution when we need it again.
So it's all about being clever and efficient. So how does this apply to our triangle problem?
Let's focus on the bottom-up approach for now. Imagine you're starting at the very bottom row of the triangle.
All right, I'm picturing it.
What's the minimum path sum to reach any number on that bottom row?
Well, you're already at the bottom row, so wouldn't the shortest path be 0 steps?
You got it. So the minimum path sum for any number on that bottom row is simply the number itself.
Okay, that makes sense. That's our starting point.
Right. That's our base case. Now let's move up to the second to last row.
Okay, I'm following along.
For each number in this row, you have 2 numbers directly below it in the bottom row.
Right.
And we already know their minimum path sums from the previous step.
Because those are just the numbers themselves.
Exactly. So to find the minimum path sum for a number in our current row, we look at the 2 numbers below it, and we pick the one with the smaller minimum path sum.
Okay, so we're basically figuring out which path down from that number will give us the smallest total sum.
Right. And then we just add that smaller minimum path sum to the value of our current number.
So we're sort of building up our solution from the bottom up, layer by layer.
Precisely. And we keep repeating this process, moving up the triangle 1 row at a time.
Okay, walk me through this with an actual example. Let's use that one from the problem description.
Perfect. So the example triangle looks like this. At the top, you have the number 2. Then in the next row, you have 3 and 4, and 6, 5, and 7. And finally, at the bottom row, we have 4, 1, 8, and 3.
Okay, so we start with the bottom row, 4, 1, 8, and 3. Those are our initial minimum path sums, right?
You got it.
Then we move up to the row above, 6, 5, and 7. Let's start with the 6.
Right, so below the 6, you have the numbers 4 and 1.
And we already know their minimum path sums are just themselves.
Right, so which one is smaller?
The 1, of course.
So to get the minimum path sum for 6, we add it to the smaller minimum path sum, which is 1, and we get 7.
Got it. So the minimum path sum to reach that 6 is 7.
Exactly. Now do the same thing for the 5 in that row.
Below the 5, we have 1 and 8. So again, their minimum path sums are just themselves. The smaller one is 1, so we add that to 5 and get 6.
Perfect. You're a natural at this. Now you just continue this process for the rest of that row, and then you move up to the next row, always using the minimum path sums from the row below.
Okay, so I keep going until I hit the top of the triangle.
Right. And the minimum path sum for that very top number will be our final answer.
Wow, that's actually pretty clever. We've solved the triangle problem using dynamic programming.
Exactly.
But wait, you mentioned something earlier about space optimization.
Yes, that's where things get even more efficient. Notice how we only ever need the minimum path sums from the current row and the row below it.
Yeah, I think I see what you mean.
We don't need to store all those previous rows calculations. We can basically throw them away.
Really? That seems a little risky, doesn't it?
Not at all. We've already used the information from those rows to make our calculations. We don't need that old data anymore.
So how do we actually implement this space optimization?
Instead of storing a whole table of minimum path sums, we can just use two arrays, one to represent the current row and one for the row below.
So as we move up the triangle, we're basically just updating these two arrays. It's like reusing the same sheet of paper.
Exactly. We're being environmentally conscious with our memory usage.
I love it. But I have a feeling there are probably some tricky details to get right when implementing this. What are some common mistakes people make?
Oh, absolutely. One of the most common is off by one errors. It's easy to get mixed up about which array you're updating or which index you should be accessing.
Right, especially with all the shifting and updating going on.
And then there are those pesky edge cases, the numbers at the very edges of the triangle where you only have one valid path down. You have to make sure your code handles those correctly.
So it's really important to be super careful with our array manipulations and pay close attention to the details.
Precisely. And that's why testing your code with a bunch of different input triangles is so important. Make sure it can handle different sizes, different values, and especially those edge cases.
Testing is a programmer's best friend, right?
Absolutely. It helps us catch those subtle bugs that can sneak into even the most carefully crafted code.
Okay, this has been a really great overview of the bottom-up approach with space optimization. I think our listeners are starting to see just how powerful dynamic programming can be. But are there any other ways to solve this using dynamic programming?
There's another really interesting approach called the top-down approach. It uses recursion and something called memoization.
Ooh, recursion and memoization. Now that sounds intriguing. I think our listeners would love to hear more about that.
Well, let's dive into that next. All right, so are you ready to explore a different way to tackle this triangle problem?
Yeah, definitely. I'm always up for learning new techniques, especially when it comes to dynamic programming.
Okay, well, this time we're going to look at what's called the top-down approach, and it uses something called memoization.
Okay, I've heard of memoization, but refresh my memory. How's that different from what we did before with the bottom-up approach?
Sure. So remember how in the bottom-up approach, we started at the bottom row of the triangle and worked our way up?
Yeah, we built the solution from the base to the top, like a pyramid.
Right. Well, in the top-down approach, we kind of flip that around. We start at the top of the triangle and recursively explore all the possible paths down.
So it's more like we're adventurers trying out different trails down a mountain, starting from the summit.
Exactly. We try different paths to reach the base. But here's the thing. As we're exploring these paths recursively, we're bound to encounter the same subproblems multiple times.
Oh, right, because different paths might converge at certain points. So instead of recalculating the minimum path sum for those points every time, we can store the result the first time we encounter it.
Precisely. That's what memoization is all about. We basically create this lookup table called a memoization table, where we store the minimum path sums for each subproblem we've already solved.
So it's like we're leaving breadcrumbs as we go down the mountain, so we don't have to retrace our steps every time we hit a familiar spot.
Exactly. And that's what makes memoization so powerful. It can turn a potentially exponential time complexity problem into something much more manageable. So picture this. You have this recursive function that's venturing down the triangle. It reaches a certain point, and it needs to calculate the minimum path sum from that point onward.
Okay, I'm following along.
But before it jumps into those calculations, it first checks our memoization table.
to see if we've already solved that subproblem.
Exactly. And if the minimum path sum for that subproblem is already in the table, our function can just grab it and move on.
No need to waste time and energy recalculating. That's brilliant.
Right. And if it's not there, the function goes ahead and calculates it. Then, of
Yeah.
course, it stores the result in the table for future use.
So even though we're using this top-down recursive approach, we're still being smart about it.
Exactly. Memoization is like adding a turbocharger to recursion.
Love that analogy. Okay, so let's get down to brass tacks. How do we actually implement this top-down solution for the triangle problem?
All right. So first, we need to define a recursive function. Let's call it calculate min path sum.
Catchy name.
And this function takes the triangle itself, the row index, and the column index as input.
So those indices represent our current position in the triangle.
Precisely. Now, inside this function, we need to handle our base cases. What happens when we reach the bottom row of the triangle?
Well, if we're already at the bottom row, there's nowhere else to go, right? The minimum path sum is just the value of the current element.
Exactly. So if the row index is equal to the last row index, we simply return the value at triangle row call.
Okay, that makes sense. It's like hitting the bottom of the mountain. You just take the value at that spot. But what if we're not at the bottom row yet? What happens then?
That's where the recursion kicks in. If we're not at the bottom row, we have two choices, right? Move directly down or diagonally to the right.
And for each of those choices, we make a recursive call to our calculate min path sum function.
You got it. But before making those recursive calls, what do we need to do?
Check our memoization table.
Of course. If we've already calculated the minimum path sum for either of those subproblems, we just grab the stored value from our memoization table and move on.
No need to recalculate.
Right. But if we haven't calculated it yet, what do we do?
Then we got to make that recursive call, calculate the minimum path sum, and store the result in our memoization table. Leave those breadcrumbs for next time.
Exactly. So now we have the minimum path sums for both possible paths, down and diagonally right. What do we do next?
We pick the smaller one, right, because we're trying to find the minimum path sum.
You got it.
Right,
And then we add that smaller minimum path sum to the value of the current element in the triangle. That gives us the minimum path sum for our current position. And of course, what do we do with that result?
Store it in the memoization table. Got to keep those breadcrumbs fresh.
Exactly. Now we just repeat this process until we reach the top of the triangle.
And to get our final answer, the minimum path sum for the entire triangle, we just call our calculate min path sum function with row and... This top-down approach feels really intuitive. Like, it's how I'd naturally think about exploring the triangle.
Yeah, it's a very natural way to think about the problem.
So we've now seen two different approaches to dynamic programming, bottom-up and top-down. It's amazing how they both solve the same problem, but from such different angles.
They each offer a different perspective on the same solution space.
It's like having different tools in your toolbox.
Exactly. Sometimes one tool might be more efficient for a particular job, and sometimes another tool might be easier to use.
So how do we choose which approach is best for a given situation?
That's a great question. It often comes down to personal preference, but there are some things to consider. Sometimes one approach might be more intuitive for a particular problem or easier to code. Other times, one approach might be slightly more efficient in terms of memory usage.
So there's no one-size-fits-all answer.
You got it. It's about understanding the trade-offs and making the best decision for the problem at hand.
But no matter which approach you choose, the most important thing is understanding the power of dynamic programming. It's like a secret weapon for solving complex problems.
I couldn't agree more. Once you grasp the core concepts, you can apply it to all sorts of problems, not just triangles.
Right. It's not just about memorizing algorithms. It's about having a problem-solving mindset.
Exactly. Thinking about how to break down complex problems into simpler subproblems and how to build up solutions from the bottom up or the top down. Those are the real takeaways here. So are you ready to wrap things up?
Well, actually, I do have one more question.
Yeah.
I'm thinking about our listeners out there who are eager to try out these dynamic programming techniques. But even when you understand the concepts, sometimes those pesky coding bugs can still sneak in.
Yeah, debugging can be a challenge, for sure.
Exactly. So before we say goodbye, do you have any advice on how to avoid some of the common pitfalls? Or at least how to track them down when they do inevitably pop up?
Yeah, for sure. Well, one thing that trips people up are, off by one errors.
Yeah, you mentioned those earlier. What are those exactly?
So these are super common when you're working with arrays.
Which is basically all the time in dynamic programming.
Right. It's easy to accidentally access the wrong element in an array. Like maybe you start your index at the wrong value or you go one element too far.
Oh, I see. So, like in our triangle problem, if you're trying to calculate the minimum path sum for a certain element, you might accidentally grab the minimum path sum from the wrong element in the row below it.
Exactly. And these tiny little errors can really mess things up. They can cascade through your calculations and lead to incorrect results. It's like a domino effect.
And what about those edge cases? The ones at the very edges of the triangle where you only have one path down,
Yeah, those can be tricky too. If you're not careful, your code might try to access an element that doesn't even exist.
like going out of bounds.
Exactly. You have to be super careful with your conditional statements and make sure you're always staying within the boundaries of the triangle. And another thing to keep in mind is the problem constraints.
The constraints.
Yeah, those limits or specific conditions mentioned in the problem statement. Like in this case, it says that the number of rows can be up to 200, and the values inside the triangle can range from negative 10,000 to 10,000.
Right. So those give us some boundaries to work with.
Exactly. And they can help you avoid issues like integer overflows or using unnecessarily huge data structures.
So basically, always pay attention to those constraints.
Definitely. They give you clues about potential issues or edge cases. And of course, the most important thing is testing. You got to test your code with a bunch of different input triangles. Make sure it can handle different sizes, different values, and especially those tricky edge cases.
Testing is like our safety net, right?
Exactly. It helps us catch those sneaky bugs that always seem to find a way in. Test early, test often, and test thoroughly. And don't hesitate to use debugging tools if you need to step through your code and see what's going on.
Awesome advice. So any final words of wisdom for our listeners who are ready to tackle the triangle problem and other dynamic programming challenges?
Don't be intimidated. It might seem complex at first, but with practice, it becomes second nature. And, it's really a powerful and versatile tool. Just don't be afraid to experiment, make mistakes, and learn from them. The more you practice, the better you'll get.
I love that. Embrace the challenge and never stop learning. Well, I think it's time to wrap up this incredible deep dive. Thank you so much for sharing your expertise and walking us through the ins and outs of dynamic programming.
It's been my pleasure. Always love talking about algorithms.
And to all our listeners out there, keep coding, keep exploring, and keep that dynamic programming spirit alive. Until next time on AI.Code.Cast, happy coding.